So this was the yesterday's um, classes conclusion, and we get these really complicated models that can be only solved or approximated by numerical methods. And and we can just move this dt to the right side and then kind of solve it that way. And the problem is, or how we can simplify it, is that some variables are changing more quickly than the others, such as like a Vm, the membrane voltage, and M, which is a sodium activation. And so we're assuming that the slow variables are constant, and these are like H and N, which are the sodium inactivation and potassium activation. So at dVm over dt is equal to 0. Obviously, Vm is not changing, so it's a null climb, which means a zero slope. And here we are defining V as a Vm, the membrane voltage, minus a V resting voltage, so that we can start from 0 rather than going from the membrane voltage of negative 70 millivolt to whatever, because it's just simpler to see it that way. And so we have this phase plane of V and M. And if we have this V null climb, which is when dV over dt is 0. And so at this very point, the V is fixed, it's not changing, because dV over dt is 0. So it can only go up and down in motion, as M can still change. And that's what it indicates. And we can also do the similar things with M. So now that dm over dt is equal to 0, and we can get some different curve on this phase plane. And these intersections between these two curves are the equilibrium points or fixed points or singularity, or they all indicate the same thing, but they are interchangeably used word. And we can kind of draw like the whole if we solve it solve for each point, we can kind of see the point and trends on how they come to whether each points are a stable or unstable equilibrium points, as commonly indicated with this ball analogy. And so this one is diverging points or unstable points, and the line that kind of goes along like that is called a separate matrix, because I think it kind of indicates the threshold condition where we've pushed it just enough to go over the saprometrics. It goes totally all the way down to the next stable equilibrium points, kind of like pushing the ball to the left, to the right, and going to the next equilibrium points. And this is at when t is equal to 0, and so these things are changing over time. And on the things are changing, like from here to, if it goes slowly to the left, and this blue line to the left, and then we only have the one equilibrium points left, so it goes all the way down to here into negative volt regime, which is how when the actual neuron signal, they go down to a below, they overshoot into below their resting voltage, and that's what it's kind of representing. And then eventually it goes back to the 0 point, or the resting voltage, and that's what this was indicating. It corresponds to this phenomenon or region. And for the Ikovich model, which is one of the models that works the best right now currently, and they're really just a mathematical model that it doesn't have a biological background that representing components, but it just really works well, and they can show a lot of different signals that corresponds to that mimics biological signals.